I'll begin. Dearly Father, we thank you for this day. Thank you again for this class, for these students. Just pray that you just guide our steps today. Help us to just understand a little bit more about tangent spaces and about how calculus theory works. Lord, in your name I pray, Lord Jesus. Amen. So last Friday, some of you guys are missing, but I would encourage you to watch what we did, if you haven't already, because we discussed how to find the tangent space. Well, really the tangent plane to surface, right? And so just to review briefly, what we learned is that if you have f of x, y, z equals to like some constant, then the gradient of f is a normal vector field. And in particular, if you have f of a, b, c equals to, ooh, that's a bad choice of letters. Let's say if you have f of, let me make this a k instead, there we go. So if you have f of a, b, c, you plug it in, you get the constant that defines your surface. Then if you take fx evaluated at the point times x minus a plus fy evaluated at the point times y minus b plus fz evaluated at the point times z minus b, well, this is an equation for the tangent plane. And the normal is given by, why is there a chair up here anyway? This is wacky. Who did this? So the normal to the tangent plane can be calculated from the gradient of the level function if you got one. But the thing is, we don't always have one, all right? Now the other viewpoint that we talked about, sort of a middle ground, is the graph, right? Sometimes our surface, we can write it as a graph. So this is viewpoint number one. Viewpoint number two, I talked about if you have z is equal to f of x comma y, then we worked out that z equals to f of a comma b plus fx a comma b times x minus a plus fy a comma b times y minus b. This right here is the equation of the tangent plane. Yeah.
Would that be z minus c up there in the second equation?
Oh, right here? Yeah, sorry about that. And then, so so for a graph, we can write the tangent plane as a graph, and technically speaking, this right here is the linearization of the function at the point a comma b of x comma y. All right, so this is the so-called linearization of f of x, y based at ab. All right, so just like in calculus 1, the tangent line is the graph of the linearization. All right, linearization of a function, you just have, a point plus a slope times, the difference of x in your base point. But since we're talking about a function of two variables, you get two pieces corresponding to the gradient here. Notice that, nabla f equals to fx, fy. This is not a normal vector field, in fact, here. What was the normal vector field? Well, the normal vector field's kind of is hiding in this formalism, right? We derived it. It was like one approach would have been, so we found that like the normal vector field would actually have been minus fx minus fy 1. And this comes from looking at f is equal to z minus little f. Or to be more precise, f of x, y, z is equal to, z minus f of x, y. So that's how we can go from the graph to the level surface perspective. And then 3, we introduced the concept, well, I wouldn't say we introduced it, but we looked at it again, the concept of a parametrized surface, right? So a parametrized surface is something like I have X, it's a mapping from some domain, which is a subset of R2, which we call the parameter space. Parameter space. And so what the parameterization does, or we could call it a patch in this case, is it lays, it lays this down as a subset of R3. So this is a parameterization of the surface S. And in this viewpoint, we found that the normal vector field at u comma v is partial x partial u cross partial x partial v. The cross product, it came back again. So this is the way we calculate the normal vector field for a parametrized surface, all right? And as I described, these partial derivatives are the partial velocities. They point tangent to the plane of the surface, right? So if you're asking what are tangent vectors, and if you have a parameterization of your surface, it's super easy to find tangent vectors. You just partial differentiate with respect to the parameter, and you got yourself some tangent vectors. So these two guys, these are both tangent to S. So, and because we can think of u and v as varying, these actually give us tangent vector fields to S, right? If we fix a point, then we've got a normal vector. Then we have tangent vectors at that particular point, and we take the cross product of those, we get a normal vector to the surface at that point. And again, you could take this and go back to the concept that I had in number 1 and write down the equation for the tangent plane from that perspective, but I won't belabor the point here. Because I want you to understand conceptually, like for viewpoint 1 and viewpoint 3, we have a way of calculating the normal vector field. And once we know what the normal vector is to the tangent plane, we already know how to write down equations for planes, right? So, any questions? So it's just a recap. So I don't think I've done examples yet in the parametric viewpoint, but here's one. If I have x of, let's say, phi theta equal to r cosine theta sine phi, r sine theta sine phi, r cosine phi, what does this parameterize? What are we looking at the parameterization of here?
Sphere.
A sphere. Now, how do you know that?
I just look at it.
You just remember it from reading the notes or something? I mean, that's a good answer. Oh, man. But let's just prove it. So if this is x, right, and this is y, I mean, how do we define a sphere? For us, the sphere centered at the origin with radius r has equation what? X squared plus y squared plus z squared equals 2? R squared, right? So what happens here if we do x squared plus y squared? What happens with the formula? Think about it in your mind. What happens? You get a sine squared and a cosine squared theta, right? So it simplifies to r squared sine squared theta, sine squared phi rather, right? Because there's a cosine squared theta plus sine squared theta. We can factor out the common term, yeah? So we just get r squared sine squared phi. And what happens when you add z squared to that? We get, lo and behold, r squared. Hooray. So indeed, yes, this is a parameterization of the sphere of radius r. And the way to come up with this parameterization, of course, is just to look at the spherical coordinate formulas and set rho equals to r, right? That's where this formula came from. Right? And this is constructed by freezing rho equals to r in our spherical coordinate formulas. So I don't want it to be dark magic to you. I want you to understand, there's a very straightforward geometric idea that led to this parameterization, right? And by the way, are there other parameterizations for the sphere? Yeah. I mean, if you're looking at the upper hemisphere, you could solve the x squared plus y squared plus z squared equals to r squared equation for z squared. Get z is equal to the square root of r squared minus x squared minus y squared. And you could look at at least the upper half of it as a graph. But I would encourage you not to do that. It's not the right way to look at a sphere by any means. This is the right way. So if we were to calculate the normal vector field to the sphere, right? In the level surface viewpoint, what would it look like? Well, we did that last time, right? So like if I take the gradient of this, right? What do I get? Well, I get 2x, 2y, 2z, right? So that is the normal vector field geometrically. But I wanted to show you the calculation. I wanted to show you how we can calculate the normal vector field from the parametric viewpoint, because this is important. We're do a lot of examples with spheres later on, guys. So like this is a calculation you want to know and have in your pocket to use, right? Although this is, I might ask you to like reproduce this result on a test or something, and it does require care. Let's go through it. My point to you, though, is that if you look at that, we should just keep in mind, like, we're expecting something like this, but it's going to look really different when we do it in terms of these formulas over here, okay? But let's keep that in mind as we're calculating as a kind of an end target to understand how that relates to what we're doing here. So we need to calculate the partial velocities. So the normal f phi theta is partial x, partial phi, cross product with partial x, partial theta. Now what are we looking at there? What is partial x, partial phi? Well, it is r cos theta cos phi, r sine theta cos phi, minus r sine phi. And then we take the cross product of that with respect to theta, which is minus r sine theta sine phi, r cos theta sine phi, and my favorite, 0. So if you're going to calculate a cross product like this, like what should you do? Should you keep r on both vectors? No. First of all, factor out the r. So there's an r here, 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 and here. We can factor out r squared, right? And then we'll use the determinant mnemonic because it's a helpful organizing device. So I'll do it here. So we've got ourselves cosine theta cosine phi, sine theta sine phi, minus sine phi. And we've got ourselves minus sine theta sine phi, cosine theta sine phi, and finally, as my favorite, 0. There we go. And so what's going on here? Looks like we've got r squared out front, and we're going to have a big old vector. For x hat, we are going to get what? X hat, so we look at this subdeterminant, right? And we get 0 for the first one, and minus, but minus times minus gives me plus, so I get sine squared phi cosine theta. All right. Just to remind you, that's coming from the determinant of this guy here, right? Let's see, what's up next? The y hat, right? So I do minus, and so I get a 0 from that, and then I get I get 4 minuses. I get 1 minus because we're on the y hat. I get 1 minus because we're on this part of the determinant. And I got 2 more here. So a total of 4 minuses in my thinking. So altogether, I got another sine squared phi, don't I? I got sine squared phi, and this time sine theta. You got to be really careful with these. It's so easy to make a mistake here. And that's the exact comment I shouldn't make because pride goes before the fall. And so I have to be really super careful on this next one, z hat. So I do this times this, which gives me cosine squared theta sine phi cos phi. And then minus and minus gives me a plus. So in fact, plus sine squared theta sine phi cos phi. All right, wonderful. Can we simplify this any? Well, obviously there's a sine squared plus cosine squared in the last term, right? So like this obviously can collapse. Do you see this? Right here, right here. And what's multiplying it is the same for both. So that just squishes down to sine phi cos phi, right? That whole thing is just sine phi cos phi. And then what's common then? Well, yeah, we've got a common sine phi across the board here, right? We could factor that out. We might as well do that. So we got r squared sine phi, all right, times what vector? Well, we have what's left, excuse me, what's left is cosine theta sine phi, sine theta sine phi, and then over here just cosine phi. Now, I haven't spent a lot of time talking about it, but what I just wrote there on the bottom line is a unit vector. Calculate the length of that vector without the r squared sine phi. Do you guys see it? What's the length of cosine theta sine phi, sine theta sine phi, cosine phi? I mean, I'm not going to, let me just talk through it. When we square this and that, we get a sine squared plus cosine squared theta with a sine squared phi multiplying it, right? So that collapses just to sine squared phi. Then sine squared phi plus cosine squared phi is 1. This is a unit vector. I have a notation for this. What is this geometrically? R hat is almost right. This is rho hat. It's the unit vector in the direction of increasing spherical radius. So this is a fine formula for it, but there's an even nicer one, which is that this is r squared sine phi rho hat. So there you go. That's the normal vector field to the sphere in the standard parameterization of it. Yep.
Is the y hat for the first one, is that supposed to be sine theta sine phi, or is that supposed to be sine theta cosine phi?
Oh, that's supposed to be cosine phi there. Thank you. I believe. Yeah. But I bet see, the reason that didn't hurt me is that's 0 there. And let's see here. Where should I have seen that? It should have come up in like this one. So I just didn't see it. I was multiplying it out. I saw what I wanted it to be. See, because I already put the sine phi, cosine phi both places. I mean, so what I wrote here is correct. It's just I had an error up there. So, yep.
Since in the last term it's sine phi cosine phi plus sine phi cosine phi, wouldn't it be 2 sine phi cosine phi?
This one?
Yeah.
But there's sine squared theta plus cosine squared theta, so that simplifies to 1. I mean,
Oh, okay, so you just factored that.
yeah, I mean, this is, yeah. That step happens over and over and over again. I did it up here too. So guys, how do you understand that this is the direction, the unit vector in the direction of increasing rho? I can think of 2 ways, right? There's the geometric way. We just think about, you know, if you're in spherical coordinates, right? And you're at this point, right? And you want a unit vector that points in the direction spherically outward, right? Then the formulas are what? X equals to rho cos theta sine phi, y equals to rho sine theta sine phi. These are just the spherical coordinate formulas, right? So if you want a unit vector that just goes out from the origin in the same direction as that point, well, you just basically look at the point back here, right? You can see rho hat as being there. And the thing is, I visualize rho hat as being attached to the point we're talking about. So you just parallel translate it from the origin out to here like that. And you can see these formulas from just simply setting rho equals to 1. See, because rho hat points to a point on the unit sphere. That's one way we could derive it geometrically. But there's another way. We could use the gradient now to calculate it, right? So how to derive rho hat? With calculus, we can let rho hat be, by definition, the gradient of the rho function divided by the length of the gradient of the rho function. And I had you guys work a homework problem to try to convince you that there's a better, like a lazier way to look at these things. Remember the g and the f squared problem, or the f and the g squared problem? I forget which it was. But like, I can look at this like this. Rho squared is x squared plus y squared plus z squared, right? So what's d rho? It is, well, 2 rho d rho is 2x dx plus 2y dy plus 2z dz, all right? And therefore, d rho is equal to x over rho dx plus y over rho dy plus z over rho dz. I think I calculated this a different way before for you guys, but this is by far faster, right? The direct approach would just be to differentiate the square root, but this is another calculational technique you can use. See, this is partial, this is what it's been, this is partial rho partial x, this has to be partial rho partial y, this has to be partial rho partial z. So what do we have? Putting this together, we have rho hat equals to, what's the gradient? Well, it's, you know, x over rho, y over rho, z over rho, right? Divided by what? The length of that, right? What is the length of this vector I'm writing? So the length of this guy right here, right, would be x over rho squared plus y over rho squared plus z over rho squared, also known as x squared plus y squared plus z squared over rho squared, also known as rho squared over rho squared, more commonly known as 1. So in fact, this is actually just this. Because it's a unit vector already. And then how do you see the formulas that I wrote down or identified in example 1? Well, use the spherical. Excuse me. See this? What's x over rho? It's cosine theta sine phi, right? What's y over rho? It's sine theta sine phi. What's z over rho? It's cosine phi. So we're back where we started again, geometrically. So you can either derive rho hat with this calculus, right? Or you can derive it geometrically, but I just want to emphasize we have two ways of thinking about it. Now, this thing I did right here is a very sneaky trick, right? Rather than just calculating the gradient of rho directly, I chose to find a related equation for rho which is more convenient to differentiate. And then I used a theorem, which is that if we write the differential of a variable as, functions times the differentials of the independent variables involved, then the coefficient of the differentials are necessarily the partial derivatives that you're interested in. Like, this is a theorem. And the theorem, just in a nutshell, let me say it in words, is that if we have an equation, we can take the differential of it, and we can use the differential to derive partial derivatives. All right? Anyway, any questions before I go on here? So we will use that later. Okay, I'm going to refer to this result when we get to surface integrals and such. Now, so example 2. Man, silly throat. So suppose you've got a sphere. All right, and maybe the point on the sphere we have is 1, 1, 1. All right. Can you guys tell me what is, first of all, if that's a sphere, what's the equation of the sphere? Question number 1. Question number 2, what's the equation to the tangent plane to the sphere at that point? All right. Question number 3, can you give me 2 tangent vectors to the plane, to the tangent plane at that point? All right, those are my 3 questions at the moment. First of all, what's the equation plane? Can you guys tell? That's the easy part. What's the equation of the plane here? X squared plus y squared plus z squared equal to what? R squared, fair enough, but if this is a point on the plane, what do we have to have? This better be 3, right? Now, you could be critical of my problem and say, you never said it was a sphere centered at the origin, and I would say, you're a math major and annoying. And number 2, you're right. Unless I tell you it's a sphere centered at the origin, there are infinitely many spheres that have the point 1, 1, 1 on them. 1, 1, 1, yeah. But this one has radius square root of 3. Fine, right? So can you guys tell me that what's the tangent vector, the normal to that? Easiest one to do is what? Do you want to adopt this viewpoint? For this question, for the tangent plane question, I don't, right? So I would go with, okay, so the gradient of x squared plus y squared plus z squared is, it's 2x, 2y, 2z, right? So if I plug in, let me call this thing f. So if I take the gradient of f and I evaluate it 1, 1, 1, I get, oh, phew, I thought it was going to be something else there for a second. I don't put 3 in 3 times. It's good. 2, 2, 2. There we go. There's the normal vector. What's the equation to the plane? So 2 times x minus 1 plus 2 times y minus 1 plus 2 times z minus 1 equals to 0. There you go. That's your equation of the tangent plane. So here was the equation of the sphere. Now, how do we find tangent vectors? Well, we could use example 1, right? So we can use example 1 to find tangent vectors, because we know that partial x partial phi, and partial x partial theta are tangent vectors, right? These are tangent vectors. Now, what's the annoying thing? Yes, they're tangent vectors, but in order to access those wonderful formulas, what do we actually have to figure out? Right. I have to figure out, I have to figure out what the choices of the parameters I need to make are in order to get that point. I chose a pretty simple point. It's a really nice point because if you think about the projection of the point down into the xy plane, what do you got here? You got this, it's 1 here and it's 1 there, right? So there's this right triangle. It's got equal length sides. What's that angle then? That angle's theta, right? So to get 1, 1, 1, we need theta equals to pi over 4, all right? And how do we figure out what phi is? So you can look at this right here, right? Let me make it bigger. So this angle is phi. So we've got 1 for the z. This distance is root 3. That's enough. That's all we need. Once we know that, we can figure out what phi is. Right? In other words, what I'm really saying is you can use this formula right here, right? You can use that in the spherical coordinates to figure out what the spherical... This is the advantage of using theta and phi as your parameters for a sphere, is you have the spherical coordinate formulas. So it's more, it's, just a warning, if you use there's like a modification of this for an ellipsoid. Did I write that down in class? I might have. If you use similar looking formulas for an ellipsoid, then you got to be careful because the meaning of theta and phi might not match up. Let me just talk about that. Let me follow this example up with that. Let me not clutter it now. So you guys tell me, what's phi equal to? Before I start talking about another example. Inverse cosine of what? Apparently 1 over root 3. Is that anything? I mean, if it was root 3 over 2, I'd know what it was, but it's not that, I don't know if that's anything particularly nice. Somebody have a calculator? It's been a while since I taught pre-calculus, so I'm a little rusty on my, oh man, what's that, 50-something? Or it just feels like it. You're going on feelings. I do need, well, I'll take degrees just for the sake of familiarity, but what we got? This is the angle. We saw this angle before. That's the angle between the vertical axis and the diagonal and the unit cube I always try to trick you guys with at the start of the course, the vectors. Okay, anyway. Now you got these, right? Wonderful. And so we can find our tangent vectors because we can plug the parameters in, like partial x, partial phi. We plug in inverse cosine of 1 over root 3 and pi over 4 for our parameters, and what do we get? I mean, I have to go back to my example 1 for my formulas. This was it, right? So and you notice that if I'm smart, I don't actually I've got a cosine phi, right? What's cosine phi equal to? It's, yeah, 1 over root 3, right? So I just put a 1 over root 3 in place of that. And what's the cosine of pi over 4? Right, or just 1 over root 2, right? So, and what's my r, my big R? R. So I've got square root of 3 divided by the square root of 2 times the square root of 3. That is, what I'm doing is I'm plugging in r is equal to the square root of 3. I have 1 over root 2 for that. I've got square root of 3 for that. And I think the next one's the same. And then the last one is what? Minus r sine phi. So what's sine phi in this context? This better be square root of 2, huh? So sine phi actually is equal to square root 2 over 3, square root 2 over square root of 3. So that's actually minus the square root of 3 times the square root of 2 over the square root of 3. So if I clean that up a bit, what we got here is 1 over root 2, 1 over root 2, and then minus, root 2. And if we calculate partial x, partial theta, what do we get? At the point, inverse cosine of 1 over root 3 pi over 4. How's that work out? So I look at these formulas, right? I have minus root 3 times 1 over root 2 times root 2 over root 3. So, was there a minus? Yeah, minus. Minus the square root of 3, 1 over root 2, root 2 over root 3. And then my middle component was root 3, 1 over root 2, and root 2 over root 3. I seem to work myself into a corner, but the good news is that's 0, right? So let me simplify it on the other side in purple. So this works out to the root 3's cancel, the root 2's cancel. Actually, that gives you minus 1, cool, 1, 0, right? So these things I'm boxing in purple, these guys would actually be in the tangent plane, right? They're in the tangent plane at that point. They'd be tangent vectors. Does it check? How can you check if they're actually tangent vectors in the tangent plane? What should they have? They should have dot product with the normal vector of 0. Do they? Is the dot product of this with the normal vector 2, 2, 2? 0? Is 1 over root 2, like is 2 over root 2 plus 2 over root 2 minus 2 root 2 equal to 0? Indeed it is. All right? And likewise down here, it's easy to see that this vector is perpendicular to that. And actually, if you stop and start thinking about the question which was asked, is this the best way to do it? Like if you want to find two tangent vectors to the normal vector, is this the right way to do it? Maybe not, right? What else could you have done? You could have just guessed a perpendicular vector. And once you've made one guess, right, you can find another perpendicular vector by simply taking the cross product of your normal vector and that perpendicular vector. That, of course, would be a more computationally simple way to do this, right? But I want to emphasize to you, geometrically, what's the meaning of the partial velocities? They actually are tangent vectors to the plane. All right. The comment I was making mid-example I should follow up on briefly. It's like if you want to parameterize an ellipsoid, right? What is the so like an ellipsoid, I'll do it up here. If I had an ellipsoid with radii ABC, if I'm like parametrizing this guy, then I can use, I can do this. I can write down this formula. But this formula is a little bit dangerous because, well, let me ask you, why do you think this, why do you think I'm saying this formula is dangerous? Maybe you've experienced this danger in a different context already. Like, there's been some problem somewhere where you guys have gotten hung up because you thought that theta had to have the same meaning as the polar angle theta. But theta is not a reserved like notation in this course overall. We sometimes use theta as just an arbitrary angle, right? Not as the polar angle in the sense of polar coordinates. Well, if I use phi and theta in this way, you should understand that unless A, B, and C are all equal, these do not comport with the meaning of theta and phi as defined by the spherical formulas. The place where 45 degree happens here will not be the place where 45 degrees happens down here. Now to fix this, if you're worried about the confusion, you could just do something like silly and slap some tildes on these angles to emphasize that, you know, they're not, they don't have the standard spherical meaning. But, or you could use S and T or U and V there. That would avoid the confusion, right? But my point to you is that by analogy, that actually is a good parameterization for the ellipsoid. And I think, oh, wait a minute. Would the same calculation go through? It would not. It's so much more hideous. Because why? A, B's, and C's are not all equal to R. The R factoring out was part of the beauty here. So many of our sine squared plus cosine squared equals to 1, they would not simplify. They just sit there. So I'm pretty sure that the formula for the n for the ellipsoid with this parameterization is quite hideous. And so like an easier way to find the normal vector to the ellipsoid would be this. Here's a hybrid approach. You could take the gradient of the ellipsoid equation. That gives you a normal vector field. And then what you can do is you can plug in the parametric formulas into that gradient, and that will give you a normal vector field. We could take a hybrid approach like that. That'd probably be the computationally easiest way to find like the parametric normal vector field to this ellipsoid. Let me work another example. Uh-oh. I'm about to erase what I haven't. Did you guys have any questions? So there's a quiz tomorrow on finding, you know, the equations to a tangent plane. And so I may test any of the 3 viewpoints or possibly the interrelation between these viewpoints. All right. And then once we're done with that, we will go on to the talking a lot more about this kind of idea that I had over here, this thing I did with the differential, trying to come to a more full understanding of that calculational technique. I've just shown you kind of the tip of the iceberg on that. Let's see here. So, oops, wrong one. So here's a simpler example for us to finish with. Suppose you've got z equals to x, e to the x squared minus y squared. So let's find equation of tangent plane at, let's say, 0, 1. Now, I guess if I say that, I should probably tell you what's the z component. If I put in 0, 1, I get what? E to the what? Almost. It'd be minus 1, right? Because y is equal to 1 there. OK, great. And so what's so I think of this as my function of two variables, right? What's fx? What's fy? Fx would be 2x e to the x squared minus y squared. Fy would be minus 2y e to the x squared minus y squared. I'm using the chain rule both times, right? Now we evaluate at the point. So like what's fx of 0, 1? What's fy of 0, 1 equal to? Well, that's easy. 0, right? What's fy equal to? Apparently minus 2 times 1 times e to the 0 minus 1. So it's minus 2 e to the minus 1. All right, so then here's our equation. Z is equal to e to the minus 1, excuse me, minus 2 e to the minus 1 times y minus 1. And that, my friends, is the equation of the tangent plane here. It doesn't have to be complicated. Like if it's a graph, we just differentiate, put it together like we derived last class, and that's it. Now I could ask follow-up questions to make it more interesting, right? Like, what's the normal vector? What's the normal vector to the plane, the tangent plane? I could ask that. I could ask you to find tangent vectors, right? Tangent vectors to the tangent plane. But anyway, and you could go back to what we did last class and look at how I found the partial velocities with respect to x and y there. That would give you an easy path to finding the tangent vectors. That would be one idea. But anyway, I think we're out of time, so I will stop.